This is a video about mathematical induction. And mathematical induction is a reasoning process that we use for lots of things in discrete math, but we're going to focus on how it connects to the recursive versus closed formulas for number sequences that we've been working on so far. And then later in the course, we'll see some proofs by induction that have nothing to do with number sequences, just so that you can see that it's generally a robust tool and not just something about number sequences. So we're going to start with this idea that we've discussed, which is that when you have a recursive formula, it's pretty easy to crank out terms, but it may not be easy to tell what a closed formula is. Now, we're not going to talk right now about how to find a closed formula. What we are going to talk about is if you think you see a closed formula for a few terms of your sequence, how do you know that that closed formula actually is correct for all time, forever and ever? So we'll start with this sequence that's written here. And to start with, we have a few to evaluate. And I would encourage you to just go ahead and evaluate these and evaluate as many as you would like so you feel comfortable with what the sequence is doing. But I'll do a few. So A1 is 1. That's given to us with the problem. A2, the reason I have the blanks here is because the way I do this is A2 is A1 plus twice 2 minus 1. In other words, the first step that I'm using when I evaluate, remember, is that I'm just writing down this recurrence relation with n equals 2. So if I take this exact thing and make n equals 2 everywhere I see it, it says A2 equals A1 plus 2 times 2 minus 1. Now I can evaluate that because I know two things. First off, I know that A1 is 1, not just because it's given there, but because it's just in the row right above. So A1 comes from the previous line as being 1. And of course, I can do 2 times 2 minus 1. That's an easy calculation. And then I just do a little arithmetic, and I get 4. So similarly, A3 is A2 plus 2 times 3 minus 1. A4 is A3 plus 2 times 4 minus 1. And it would go like that for a while. In each case, the first thing I need to do to evaluate these things is I need to know the value of the previous term, and I just look up there and grab it. So A2 is 4, because it says so before. And 2 times 3 minus 1 is 5, and together that adds up to 9. And then finally, A3 is 9, and 2 times 4 minus 1 is 7, and so I get 16. So feel free to pause and do more of those if you would like. What I'll do is just point out that it looks like there's a formula that I could propose for these terms because I know that these all look like perfect squares. And so 1 squared, 2 squared, 3 squared, 4 squared as a formula seems to fit the sequence that I'm getting. And so it's kind of weird because I'm following just the recursive sequence, and I can do that for as long as I want. And every time it seems like I'm getting a perfect square, getting the next perfect square. So the idea of this proof is that we're going to say, if I know for a fact what the recursive description is, in other words, I know I can keep doing this forever, but I just don't want to have to, and I think that I know the formula, and the reason I say think is because I can only check the formula as far as I have generated some examples. So it's sort of like I've generated some data, and so far the formula here fits the data. The question is, how do I know going forward, forever afterwards, that that's still going to fit? And that's what requires a proof. Just one more example, just to illustrate that we really do have this pattern in this case, or at least support that we do. We can jump down to like A17. So suppose I know A17 is 289, and that is 17 squared, by the way. Can you find A18? And so really, if I just do those steps that I was just doing, then I can see that I can check this without having gone all the way down to the table. I really can just jump in at any point and see how this works. That's what the original recurrence relation would say. This recurrence relation would say if you made n equal to 18, A17 is 289, so I'd have to know that somehow. 2 times 18 minus 1 is 35, and so together that adds up to 324. And if you check, you can find out that 324 really is 18 squared. So what this is saying is, if you were to drop down in the list and for some reason, whether someone checked it for you or you checked it yourself, for some reason knew that a sub 17 was 17 squared, 289, then you could just use the recurrence relation to find the next term, and it turns out that it is 18 squared. So it really does seem like wherever you drop down in this list, if you know you have a perfect square at some point, then just following the recursive pattern will show you that you get the next perfect square. And so the only thing left to do is if we want to make an argument in general, we don't do that by just throwing out random things like 17 and 18. We want to write this for the reader and let the reader decide which term I'm on. And that means letting an m be given that has different properties. And then we move on from there. So that's how we're going to structure the proof. We do have to have the reader be allowed to pick where they're checking, like what is the next place to check. And so that's what we need to do to wrap up the structure of an induction proof. All right. So here's the task. We're given that we have this recursive description. So we know that that's how we can generate terms forever. And we think that we notice that it has this pattern. So we claim that this pattern is also satisfied. That's the position that we're in. Okay, so the trick to mathematical induction, and this is true regardless of whether we have number sequences or not, is that we imagine the things that we're trying to check. Remember that what we're trying to check is a sub n equals n squared. So rather than try to prove that by just saying to the reader, let n be given, and I will address whatever row you're on, what I'm going to do when I say it's a proof by induction is I'm requiring that the reader check all of these statements in order. And so the reader is buying into the idea that they're going to be checking, in quotes, an infinite number of infinite number of statements, but they're going to check them in order. They're going to check the a1 equals 1 squared first, and then the a2 equals 2 squared, and the a3 equals 3 squared. Notice we've never required the reader to do that before. With our other proofs, when we say let n be given, they can pick any number they want. If we say let an odd number be given, they can pick any number they want. All we're saying here is I'm going to ask that you check all the statements in order. So if you say, I want to check 15, that means you're going to check the first one, the second one, the third one, all the way through the 15th one. It's requiring the reader buy into a way of thinking, but it is sufficient for proving the statement. At the end of that process, you still will have proved whichever statement they've said. It's just that you're requiring them to check all of the ones up to that as well. So we're going to use a table early on, and I'll show you what a paragraph looks like at the end because we don't really want to have to write tables all the time. But the table helps organize your thoughts a little bit to get the right mental image of what's going on. So we are, again, we know the recursive formula. I don't have it written down here, but we've already talked about that. So this is what we did before. Those were our steps to generating the sequence values. And over here we have the closed formula values, 1 squared, 2 squared, 3 squared, 4 squared. So this is exactly what we had written before, but I'm kind of putting it in a tabular form. So the idea is here, I'm really just using the recurrence relation to generate terms. Here I'm saying what the closed formula would be. And my last column here, the reason I have a question mark there is because I'm going to just check off that those are the same. So every time I'm getting the same answer, so 9 plus 7 is 4 squared, yes. 4 plus 5 is 3 squared, yes. Right. So when these are equal, then I'm putting a check mark there. And so you can continue that as far as you want. And so if you'd like to continue further, again, pause the video and do a few more. But you see, I just put et cetera, blah, whatever, because it doesn't matter how many you do. So you start off, so as the reader, you are checking as many of these as you want, but you're checking them in order, meaning the first, then the second, then the third, then the fourth. So now, as the reader, if you have been checking those things in order, I can now say, let M represent the first row number not yet checked. So regardless of how many rows you just checked in the table, there is a first row you have not yet checked. And so that's what M represents in the induction proof. And that's very important because that's stressing the idea that the reader has checked all the stuff in order. So I'm not just jumping down to any row. I'm saying M is, when I say M is the first row not yet checked, that implies that you have checked all the stuff before that. So the table would look like this. And if you really just check the 4 statements that I did on the previous slide, then your M is 5. If you paused and went ahead a little bit more, maybe your M is 10. Maybe you're on the 10th row and you've checked all the ones before that. And so I don't know, but it doesn't matter, right? I'm going to explain to you why this next row has to be checked out, has to get a yes here, even without knowing how far down you've gone. So this is really the key thing, is that when we think of this as a table, if M is the first row that we have not yet checked, that means your table is completely full up to that point. And so in particular, the row before that, the row that you would label M minus 1, would have something here, A sub whatever it is in it. It would have some calculations like this. And then here it would have M minus 1 squared. And most importantly, it would have yes here that we've checked, that whatever these calculations are match the perfect square as they're supposed to. So that's the situation that we're in an induction proof. M is the first row that hasn't been checked. We're ready to check M now, and the table above us looks like this. It's completely filled in, and to the point where we have a yes here that we really have already checked that whatever this calculation did ended up being equal to this. And that's all we need. So here's how we can fill in the next row. The next row would start off with A sub M. And one of the valuable things about really checking a few of these rows is that you have to think about what you're doing. And so all I'm going to do here is exactly what I did up here. So up here I said A3 was the previous row plus this formula. That came from the recurrence relation. And so that's my first equal sign here. It's just whatever the recurrence relation says. Right, that's literally what the recurrence relation said. And that's what I did in these statements up here. First wrote down what the recurrence relation said. My second equal sign up here came from looking up to see what the previous value was and then doing the arithmetic here. So looking up to see what the previous value was, that is saying what is AM minus 1? Well, if you look up here, AM minus 1 was some calculations, but ended up being equal to M minus 1 squared, right? We have a yes here, that this calculations were equal to this. And so since I'm about to write an algebra expression down, this is definitely what I want to use, not whatever these weird calculations were. So A sub M minus 1 is M minus 1 squared. And inside the parentheses here, there's really not a lot of, like here I could just do the arithmetic in my head, but there's really nothing I can do algebraically to simplify that at this point. So I'll just write that down. So the first equal sign is the recurrence relation. The second equal sign is by looking up at the previous row of the table. Okay. So that's what's called the induction step. After that, we're just simplifying algebraically. So M minus 1 squared is M squared minus 2M plus 1 plus 2M minus 1. And then stuff cancels, cancel, 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 cancel. And we end up with just M squared. So the recursive formula simplifies to say A sub M equals M squared. The closed formula says I'm supposed to get M squared, and I did. So what we've shown is that if M is the first row that the reader hasn't checked, this argument is walking the reader through why that next row has to also be checked, has to also be true. And so the logic of it is, just imagine that you literally check the first 9 rows, then this argument that we just gave would tell you why the 10th row also checks out. But now you've checked the first 10 rows. And so this same argument with M equals 11 now tells you why the 11th row checks out. And now M is 12. 12 is the first row you haven't checked. And so if you read this argument again, with M equals 12, it would tell you why the 12th row checks out. So whatever point you're at, this same argument using that value of m will tell you why that row gets a yes. Why that row for that row this statement is true. The a sub m that comes from the recurrence relation is equal to the formula for the closed formula. And so because of that, that's what mathematical induction allows us to conclude, that the statement must always be true. It must always be true that the recursive formula is giving us the same thing as the closed formula. Just finally, if we write this in paragraph form, this is what it looks like, and I would encourage you to read through this and make sure you see how it really captures all of the pieces that we just talked about. And then on whatever day next week we talk about this, we'll work on some other proofs, and we'll start off using the table form to kind of organize our thoughts. But eventually we'll want to work towards things being in paragraph form, and that'll help us also not have this be sort of hopelessly attached to statements about sequences of numbers. We'll be able to use this reasoning technique for other kinds of discrete objects as well.